Okay, one more time. Sorry, my storage on my phone keeps filling up and I couldn't figure out why. So anyway, that last video left off with us saying that our noble gas configuration for potassium and zinc, we don't have to rewrite that because it's exactly the same as before. Okay, so for the dot diagrams, hydrogen, carbon, nitrogen, sodium, chlorine, and potassium, all of those, we know a trick now. I gave you guys that chart to remember where you just take the last digit of their group number and that'll tell you how many dots to give them, okay? But what do you do in the case like with zinc? Zinc doesn't fall into that category. Remember that transition metals have variable oxidation states, and that's because they have different amounts of valence electrons. So for zinc, to figure out how many valence electrons it has, we will have to look at its electron configuration. So the thing I'm looking at are the coefficients, so the 3 and the 4. Remember that valence electrons are in the outermost energy level, so you're going to have to look for the one that has the biggest coefficient or the highest number. And in this case, that would be the 4th energy level. So we have 1, 2 electrons that are in its highest energy level. Okay, all right, now for electromagnetic radiation. The easiest way to remember the order from lowest energy to highest energy of the 7 different types is the way I'm going to show you. Okay, so practice writing this out a few times, and it would even help to, as soon as you get your test, go ahead and write this out. That way you have it there for you, for your reference. Okay, so in the middle, there's 7 types, right? In the middle, that's visible light. And the colors of visible light you can remember by Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Now, all together, we call that visible light, right? That's what our specialized cells in our eyeballs can see, in our retinas, right? Okay, so then this V is for violet. So in front of violet, we put ultraviolet. This R stands for red, so right in front of it, we're going to put infrared, or IR. After ultraviolet, this is the high energy side, which also corresponds to a high frequency, which also corresponds to a low wavelength, okay? The ones that is even higher of energy than ultraviolet is going to be X-rays. Right, that's why you have to kind of limit how many X-rays you get in your lifetime. Too many of those rays can be damaging to tissue. Okay, and then the highest energy of these is going to be gamma. Okay, down on the low energy side, again, if we have low energy is equal to low frequency. And we can also equate that to long wavelengths. Okay, remember the long wavelengths kind of move slowly. The short wavelengths move very, very fast. Okay, so in front of the infrared, we're going to have microwaves, and we're also going to have radio waves. Okay, so again, practice writing that out in that order. If you start with Roy G. Biv in the middle, ultraviolet next to the violet, infrared in front of the red, and then on the other side of infrared, we have radio and micro, and then X-rays and gamma on the high energy side. Okay, practice writing that a few times. All right, so then what is the mathematical relationship between those 3 variables? Energy, wavelength, and frequency. Energy and frequency, this is a mathematical relationship, and you have 2 options. You're either going to call it directly proportional, or it's going to be indirectly proportional. And the difference of those two is whenever you're comparing variables in an equation, a direct proportionality means that both of the variables increase or decrease directly, meaning one of them increases causes the other to increase automatically. An indirect proportional relationship is where one variable will increase while the other variable decreases. Okay, so how does that relate to our energy, wavelength, and frequency? Well, energy and frequency are directly related, so those are going to be a directly proportional relationship. And what that means is that as energy increases, so does the frequency. They could also both decrease, but the idea is that they're moving in the same direction. Okay, and energy and wavelength are indirectly proportional, which means, again, if energy increases, that will cause the wavelength to decrease. Wavelength and frequency are also indirect. And so as wavelength increases, that will cause the frequency to decrease. The other word for indirectly, and I don't know what word they're going to use to describe this relationship. It's either going to be indirectly or inverse, or inversely, if you will. Okay? All right, this next part is now looking at these pictures to determine the different relationships, okay? So which of the following has the longest wavelength? Well, that's the one that has the longest space between the slopes. And that's going to be this one, number 3. Right? It's actually showing you the measurement of wavelength is the longest here. Which one has the highest energy? Again, what we're looking for is short wavelengths, the ones that move really, really fast up and down. And that's going to be number 2. Okay. Which of the following has the lowest frequency? Again, that relates to a very long wavelength. So again, the answer is the 3rd one. Okay. Now for page 5, looking at periodic trends. Okay. This page you need to memorize, like literally, okay? It's hard to guess what kind of question is going to be asked, but we've gone over all this except for, like I said, metallic bonds here, okay? So just spend some time really knowing the information, okay? There's not much more you can do with that, okay? All right, so then for periodic trends, let's remember the relationship, or the properties, I should say, for metals, nonmetals, and metalloids. Notice that the other way we call metalloids is called semimetals, okay? Or we could also use the term semiconductors. Okay, so properties of metals. Some properties of metals is that they're shiny, they're malleable, which means they can be made into flat sheets. Think of like aluminum foil, right? They're ductile, which means they can be made into wires, right? Like when I open an electrical wire, inside of it is a whole bunch of little copper wires. So ductile, or ductility. The next one, it can conduct heat and electricity. Some examples, common examples, gold, copper, aluminum, etc. Okay, so then properties of nonmetals. Nonmetals are going to be dull in appearance, and they can also be brittle. Brittle means that they will shatter under pressure. Okay. You could think of like the pencil lead that's in your mechanical pencils, right? How they always break. Well, that's because they're made out of graphite, which is carbon. So, just consider when you put too much pressure on your pencil, it causes it to break. That's because it's brittle, okay? Dull appearance just simply means that it's not shiny. Poor conductor, or a non-conductor of heat and electricity. And again, some examples here are graphite, carbon, oxygen, and nitrogen. Another important thing to mention here is that a lot of, not all of, but a lot of nonmetals are gaseous. They could also be solid, and there's one liquid, but for the most part, they tend to be gases. Okay, and then properties of metalloids. Again, metalloids we also call by the name semimetals or semiconductors. These have properties of both the metals and the nonmetals, hence the name semimetals. Some examples are silicon, which has a shiny appearance, and it also conducts electricity like metal. Okay, the next one. we have atomic radius. Remember that that's the distance from the nucleus to the outermost electrons. In class, I gave you guys the snowman analogy, and we said that if you built a snowman, it would start off small on the top and get larger on the bottom. And if you knocked him over, it would follow the opposite trend, right? It would get smaller as you go over. Okay, so going down the group, the energy levels that are being added cause the atom itself to get bigger. Going across the period, they get smaller because you're not adding energy levels, but you are increasing the effective nuclear charge. See page 32 for additional information in your notebook. Okay, periodic trend for atomic radius, again, just as I got done saying, it will increase going down a group because we're adding more protons and, and we're adding energy levels here. That's what it should say, energy levels. More energy levels means that the atom automatically gets bigger. Decreases from left to right along a period, again, because the effective nuclear charge, or what we called ZEFF, is increasing the number of protons compared to the electrons, so it's going to decrease the radius. Oh, okay, for ionic radius, having to do with cations or anions, remember that cations lose electrons, so they're going to have a smaller radius than their corresponding atom. An anion, on the other hand, gains electrons. So in order to accommodate all the extra electrons, it's going to have to get bigger. Here's an example. Sodium atom compared to sodium ion. You can see that it loses one electron and the atom itself gets smaller. For the opposite, chlorine from the atom to the ion will get bigger because we are gaining an electron. Okay, for metallic bonds. Metallic bonds, I want you guys to remember the phrase sea, like the ocean, right? Sea of electrons. And when you look at this picture here, notice how the electrons are all kind of spread out. They're not really connected to any of the atoms themselves. Well, that actually turns out to be pretty important when we look at the properties of metals. The sea of electrons are also called delocalized, that's this word right here, delocalized electrons. And what that means is that they're not fixed in a specific atom. Instead, they can actually shift or move throughout the entire metal. So an electron that starts way over here can travel way over here. That explains a lot about the characteristics of metals. One, metals conduct heat and electricity because, let's say this electron at the very end of the metal gets hit with some electricity. Well, all it's going to do is just continue traveling through. So the ability for these guys to kind of move through the entire structure is going to allow them to transfer that energy. Okay. Additionally, metals are malleable and ductile because electrons are holding all those atoms together, but not in a too rigid way. So anytime you get a question asking you about the reason metals have a specific property, it's because of the sea of electrons, okay? All right, that concludes page 5. We have one more page to go. Please see the next video.